Lately, Flerfers, especially Anthony Riley, aka Sleeping Warrior, aka Prattling Dipshit, have been banging on about buoyancy and talking about density as though it's a force and pretending to know what they're talking about. Clearly they don't. Given that fact, I plan to go on at tedious length about it until hopefully at the end of this they'll understand it or everyone is sick of hearing about it. Word of warning, math ahead. If this frightens you, turn back now. The first thing I need to talk about is pressure. What is it? What causes it? Imagine a rectangular container with sides of length x and y filled with water. I'm using water in this example, but the following holds true for any fluid. On the water's surface, there's no pressure. I'm ignoring air pressure because I'm only interested in how much the pressure will change. Now we add water to increase the depth of the water by an amount d. So the total volume of water added is V equals x times y times d. I'll call the density of the water rho because in physics we use Greek letters a lot. So the total mass is m equals v times rho, or m equals x times y times d times rho. The downward force, F, caused by this water is its mass times the acceleration due to gravity, g. So the total downward force is F equals x times y times d times rho times g. The pressure, P, is the force F exerted by the water, its weight, divided by the area of the container, P equals F over A. We've already calculated the force, and the area is just x times y, so P equals x times y times d times rho times g over x times y. X and y cancel from the top and bottom, giving us the formula for pressure. From this, one might conclude the pressure is pushing down. After all, the force from the added water is pushing in that downward direction. This would be an incorrect conclusion. Imagine a piece of paper at some depth d. What are the forces on the paper? There is the force of the water pushing down, but there is an equal pressure pushing up on it. Otherwise, the paper would be accelerating downward. F equals ma. Pressure is a force pushing in all directions. Now that you have a basic understanding of how pressure works, let's see what affects objects within the fluid. Imagine a brick with dimensions x by y by z submerged in a fluid. What are the forces on it? FYI, most of physics is about balancing of forces. I'll call the force on the top of the brick Ft, the force on the bottom of the brick Fb, and the weight of the brick W. Ft, the force on the top of the brick, will be the pressure at the top of the brick multiplied by the area of the brick. Ft equals Pt times x times y. I've already given the equation for pressure, so the force pushing down the top of the brick is the depth at the top of the brick multiplied by the density of the fluid multiplied by the acceleration due to gravity. Ft equals dt times rho f times g times x times y. Similarly, the force pushing up on the bottom of the brick is Fb equals dB times rho f times g times x times y. The weight of the brick is simply its volume times density times the acceleration due to gravity, so W equals x times y times z times rho b times g. Given this, the total force of the upward pressure at the bottom of the brick minus the weight of the brick minus the downward force on the top of the brick. I know that in the real world a brick is denser than water, so the force will be down, but this would simply mean a negative force upward. So the observed weight, WO, would be given by the equation WO equals dB times rho f times g times x times y minus dt times rho f times g times x times y minus x times y times z times rho b times g. We can simplify this by recognizing that the first two terms are nearly identical and combining them. Yes, there are similarities with the third term, but we can deal with this later. For now, I'll just simplify the first two terms. WO equals dB minus dt times rho f times g times x times y minus x times y times z times rho b times g. But we know that the depth at the bottom of the brick, dB, minus the depth at the top of the brick, dt, is just the thickness of the brick, z. This gives us rho f equals g times x times y times z minus x times y times z times rho b times g. For simplicity, I'll set the volume of the brick Vb equal x times y times z, so the observed weight of the brick is WO equals rho f times g times Vb minus rho b times g times Vb. This equation has two terms. The first term is a positive value, the second is a negative value. Since I define positive as up, the first term is an upward force. The magnitude of this force is simply the weight of the water that was displaced by the brick. This is the buoyant force. The second, negative term, is just the weight of the brick acting downward. We can combine these two terms, giving us WO equals rho F minus rho B times G times VB. From this, we can see that if the density of the brick is greater than the density of the water, the upward force is negative, so the brick will go down. If the density of the fluid is greater than the density of the brick, for example, if the fluid is mercury, the total force will be positive, so the brick will go up. If the densities are equal, there will be no net force. This is called neutral buoyancy. So we've seen that the buoyant force for a simple object like a brick is just the weight of the fluid that's been displaced by the brick. The next question is, does this work for any object? The simple answer is yes. The more involved answer is, let's find out. For simplicity from this point forward, I'll denote the difference between the density of the fluid and the density of the object in the fluid, rho F minus rho O, as delta rho. If it's positive, the fluid is denser than the object. If it's negative, the fluid is less dense. Start with the brick. The equation for buoyancy only depends on the volume of the brick, not its actual dimensions. Given this, I'll make the brick long and thin. It will have a height h, and its x and y dimensions will be arbitrarily small sizes delta x and delta y. Next, stick a bunch of bricks of different heights together in an m by n grid. Each brick will have a height hmn, and thus volume vmn equals hmn times delta x times delta y. From this, and the buoyancy equation, each brick will have an observed weight that can be expressed as wmn equals delta rho g delta x delta y hmn, or wmn equals delta rho g vmn. The total weight of the bricks will simply be the sum of their individual weights. Wt equals sum over m and n of wmn, or Wt equals sum over m and n of delta rho times g times vmn. Since density and gravitational acceleration are constant, they can be taken out of the summation, so Wt equals delta rho times g times the sum over m and n of vmn. The sum of the individual volumes is, of course, the total volume V. From this, we get back to our original equation, Wt equals delta rho times g times V. This confirms that the equation for the total buoyancy for an object made of smaller regularly shaped objects is the same as the equation for a single regularly shaped object. This is good, but we're still dealing with rectilinear bricks. What if we have an arbitrarily shaped object? Consider an object of extent x by y and a thickness at any point t of xy. We can break the object down into infinitesimally thin bricks with dimensions dx by dy. Each of these bricks would have volume v of xy equals t of xy dx dy. To find the total buoyancy, we would need to change our summation into an integral. Wt equals delta rho times g times the integral of t of xy dx dy. Since this integral is just the totaling of the volumes of the infinitesimally thin bricks within the object, the integral is just the total volume of the object. Wt equals delta rho times g times v. To clarify this a bit, let's use a specific example, a sphere. To calculate the buoyancy, I'll need to switch to a more suitable coordinate system. In this case, polar coordinates will be easier to work with. Doing this, we consider a sphere with radius capital R. Its thickness at any distance r from the center, tr, will be tr equals 2 root big R squared minus little r squared. This is just Pythagoras' theorem. Because of the symmetry of a sphere, the distance from the center is the only variable on which the thickness depends, so by switching to polar coordinates, I've changed my dependency from 2 variables to 1 variable. Plugging the thickness equation into our integral and converting the integration to polar coordinates, we get Wt equals delta rho times g times the integral from r equals 0 to r times the integral from theta equals 0 to 2 pi tr r dr d theta. I'm not going to go into how the conversion to polar coordinates is done. If you're really interested, you can Google it. Theta and r are independent of each other, so they can be split into 2 integrals. Wt equals delta rho times g times the integral from 0 to 2 pi d theta times integral from r equals 0 to r tr r dr. The integration over theta is just 2 pi, so Wt equals delta rho times g times 2 pi times the integral from r equals 0 to r tr r d theta. Now I can substitute in the equation for tr. Wt equals delta rho times g times 2 pi times integral from r equals 0 to r of 2 root r squared minus r squared r dr. I could bring the 2 outside of the integral. This gives us Wt equals delta rho times g times 4 pi times the integral from r equals 0 to r of r root big R squared minus little r squared dr. The remaining integral looks ugly, but it's fairly solvable. For clarity, I'm just going to focus on this integral without worrying about its bounds. I equals integral of r times root capital R squared minus little r squared dr. To simplify this, I'll make the substitution u equals big R squared minus little r squared and take the derivative of this. Du by dr equals minus 2r, or du equals minus 2r dr. Substituting this into the integral gives us I equals minus 1/2 integral of root u du. This integral is easily evaluated. I equals minus 1/2 times 2/3 u to the 3/2, or I equals minus 1/3 u to the 3/2. I know there should be a constant added to this, but since I'll be applying bounds to it, the constant will cancel out anyway. Now it's just a simple matter of putting in the value for u and applying the bounds. I equals minus 1/3 big R squared minus little r squared to the 3/2 from r equals 0 to r, and then evaluate this. I equals minus 1/3 big R squared minus big R squared to the 3/2 minus big R squared minus 0 to the 3/2, which simplifies to I equals 1/3 r cubed. Finally, after all of this, I can shove this back into the original equation and get Wt equals delta rho times g times 4 pi times 1/3 r cubed, which simplifies to Wt equals delta rho times g times 4/3 pi r cubed. In case you don't recognize it, that last term is the equation for the volume of a sphere. So, once again, we find that the observed weight of the object, when buoyancy is included, Wo equals delta rho times g times v. Or its observed weight will be its actual weight minus the weight of the displaced fluid. In a recent video, Sleeping Warrior, aka Prattling Dipshit, did an experiment that he claims proves that density is a force. Basically, he says, I changed the density, this caused the egg to move, therefore density is a force. First of all, I'll ignore the fact that Sleepy Dipshit is an arrogant, condescending twat. In science, personality is irrelevant. Newton, after all, was a crackpot who believed in alchemy and astrology. He also tried to erase Robert Hooke's scientific contributions from history. That doesn't make his findings about gravity incorrect. It doesn't invalidate his equations of motion. Yes, Newton was a bit of an ass. Similarly, despite the fact that Sleepy Dipshit is also an ass, all that matters is the experiment. So let's look at it. Has anyone figured out why he's dressed like a butcher? What exactly did Dinglenuts do? His experiment in a nutshell, or case, is dropping an egg into tap water and seeing that it sinks, then dropping it into salt water and seeing that it floats. What he showed is that an egg sinks in tap water but floats in salt water. All he did is show that the salinity of the water affects the buoyancy of the egg. So, by his logic, salinity is a force. Sleepy tried to demonstrate that the salt water is denser using a dissolved solids meter. Unfortunately, a dissolved solids meter doesn't measure density. For this, Sleepy has received a lot of criticism, but I'm not too fussed about it. His only goal was to show that the salt water is denser than tap water, and as long as he's not using it for quantitative measurements, a dissolved solids meter will adequately demonstrate this. At this point, all he's done is show that there is a relationship between the density of the water and the buoyancy of the egg. Since he's not doing any quantitative analysis, all Sleepy is doing is making a qualitative observation that a denser medium will cause the egg to float. In terms of the scientific method, all this would allow him to do is formulate a hypothesis, which is what he does. Dipshit hypothesizes that density is a force causing the egg to rise. He offers no mechanism by which this would occur. All he does is claim that his hypothesis is proof of his assertion. That's not science, but let's continue. Sleepy Dipshit has tackled one of the first parts of the scientific method. He made observations to formulate a hypothesis. The next step is to develop a theoretical framework explaining these observations. I've just provided this. You're welcome. Now it's up to Sleepy to do the experiments to confirm or refute this theory. This would require actual measurements of the densities of the tap water and the density of the salt water, or preferably densities of multiple samples of water with varying salt concentrations. This isn't too difficult. All he needs to do is mix up some batches of salt water at varying concentrations, measure a liter of each, and weigh them. This will accurately get the densities of the salt water samples. Next, Sleepy needs to get the density of the egg. This too is simple. Weigh the egg, get its mass, then submerge it in water to see how much it displaces. This will give its volume from which density can be calculated. The next part is a little tricky. Dipshit needs to find a way to weigh the egg while it's submerged. I suspect a spring scale of some variety would do an adequate job of this. If so, the original measurement of the mass of the egg should also be taken using the spring scale. This would ensure that any errors introduced by the inevitable inaccuracies of the scale would be the same for all measurements. With these preliminaries out of the way, the next part is to conduct the actual experiment. Knowing the densities of the water at various salt concentrations and the density of the egg, these values can be entered into the equation I provided to get the predicted weight of the egg. Finally, weigh the egg while it's submerged in each water sample and compare the actual weights to the predicted values and see if it falls within experimental error. The experimental error part can be complicated. Let's take, for example, the calculation for the density of water. Measure 1 liter of it. If the scale on the vessel used for measuring is marked in 10 milliliter divisions, all that can be said is the water is 1,000 plus or minus 10 milliliters. Similarly, if the scale being used to weigh the water is only accurate to 0.1 grams, and the water weighs 1,000 grams, all that can be said is the water weighs 1,000 plus or minus 0.1 grams. So the actual density would be within the range of the highest possible value and the lowest. This would place the density of the water in the range of 0.99 kilograms per liter and 1.01 kilograms per liter. Similar calculations would need to be carried out for every measurement. Finally, once all of this is completed, and even if the results were exactly as predicted, it is still impossible to unequivocally say that the theoretical framework that I provided is proven. All that can be done is to say that it is not incorrect. If, on the other hand, the results were inconsistent with the equations, it can be concluded that the theory is incorrect. On the other hand, if Sleepy Dipshit has a competing theory about what causes buoyancy, he should provide a detailed theoretical framework that makes specific testable predictions and carry out quantitative experiments to verify or refute these predictions. Well, Sleepy, ball's in your court. Are you up to the challenge? Can you prove me wrong? Can you provide a competing theory about what causes buoyancy? I didn't think so. Anywho, if you liked this video, click that like button. If you didn't, don't. I won't lose sleep over it. Until next time.
If there's a concrete wall in front of you, go through it, go over it, go around it, but get to the other side of that wall.